code, and it is also the daily problem for today. Okay, jump game 4 is very closely related to 3, I would say. Yeah, 3, the one that we did yesterday. It is the same approach. So the one that I showed yesterday, you just need to make a couple of changes to it and it will work the exact same in this case. Now what do I mean by this? So I'll just put the question down very simply. I've explained it in more detail in part 3. You should definitely watch that. But in this question, the options that we have now are, there's 3 options, all right? I plus 1. So from the index that we were on to index plus 1, I minus 1. Keep in mind we can't go out of bounds. So we will say in bounds, right? And the next thing, the new interesting thing is we can move on to an index j only if the value at j, so array j, is equals to array I. Okay, so we've pretty much covered a similar issue over here in jump game 3, right? We were able to jump the index plus the number of the element. In this one, all we have to do is index plus 1 and index minus 1. We have to just consider those two, but that isn't the main crux of this question. I would say this part is the third option that we have open now. So okay, if we're told that we were at index 1, right, and let's say at index 3 we were given the same value, how would we store the index at which a particular value occurs? How do we store multiple indexes at which a particular value occurs? If we said hash map, good thinking. What we do is we have a hash map, and what we do is we give an n, right? We keep the element as the key, and sorry, not a list, that you will interpret that as a list, and we have n as the key. And what we can do is we can store the indexes at which point this n occurs repeatedly, and this essentially is now our third option. Third option in the sense that we will loop through this. This is possible places that we can go to, right? And our goal over here is len array minus 1, right? Our index has to be equals to the goal, right? And considering this idea now, this particular idea, we should be able to explore all the neighbors, and we should be able to consider these two, I plus 1 and I minus 1 cases as well. And keep in mind, I said neighbors, right? Well, it's because we are doing a BFS approach on this one, okay? I don't think a DFS is even possible in this scenario. A DFS would require going in depth into like a particular path. I would say BFS is definitely the better way, because what we have to do is keep track of the amount of steps. So we need a counter of steps. And if you've done BFS questions before, then if you've done a tree question, which is like get the depth of the tree, I think I've covered that on this channel as well. If you have the depth of the tree, you know what we did in that. So you do like a simple for loop, right, for I in range len of q, and whenever that like particular for loop ends, you are now in your next like level, okay? So we do counter plus equals to 1, and it's pretty much the same. So if we have like index 1, right, our two options are like 2, 0, and let's say some value at 5 occurs. All we have to do is this will be 0, this will be 1, kind of like that. Get what I mean? So when the length of the array itself, this is the edge case by the way, if length of the array is 1, we return 0, because that is the depth that we were at right here, right? Okay, now there's a bit of a tweak, right? Like I said, we have to do a for loop for the well, we have to set up a hash map. So let's call that indexes, right? And also do keep in mind, write this down, but yes, indexes over here, default. So what we will do is we'll make it like list for the values, and then what we can do is store all of the indexes at which a same value occurs. All right, now that we have this set up, we'll do the same exact procedure as we did yesterday. So visited set, right, we have a set of visited, we will do visited dot add 0, right, because the first thing that we do is explore. Keep in mind, we are not tracking the indexes anymore. What we are doing is we're going from 0 to some x to some goal. Okay, so our visited will start off with 0, and we will also dequeue the 0, right, so that we explore it first. Now let's consider our levels. So our level starts off at 0, and like I said, the same for loop, the same while loop, and then we do the same for loop. So for dash and range, whatever you want to name the variable, we don't really use it, but what matters is this for loop itself, right? Okay, and just to make a note, I will write down counter plus equals 1 over here somewhere so that I remember it while I explain this. Okay, like I said, so the last thing we did yesterday was we pop off the index, so q.pop left, right? And now we have our neighbors that we want to consider. But before we do that, we will just check, is the index that we are on right now equal to the goal? If it is, then return counter, right? Whatever level we were on, just return that. Now we have an array of possible indexes that we can visit, right? And we want to visit them all, right? It is a BFS question. We want to visit them all. When we have a node, right, and it expands onto like some neighbors in BFS, what we consider is, well, we will consider this on one level, but in the next iteration we will indeed consider all three together at once. It's not like DFS where you go like this, like this, like this, right? You don't go like this. No, you do one node at a time, and then every single neighboring node you do it at the same time on the next iteration. So now that we have that out of the way, I'll erase that. We have potential neighbors, right? So we can say for entry for neighbors in indexes, and corresponding to the index that we are on, so the number we get from that index, right? And we will only add it if it makes sense to add it. So if entry not equal to the index that we were on, and entry not in visited, right? Because it wouldn't make sense to just keep adding, otherwise you would just have an infinite loop pretty much. So visited dot add this entry, we will explore this neighbor no matter what. Q dot append this entry as well, right? Now we have to process it, but that's out of the way. Now another small trick in this question, right? You will have all of this set up, you will have all of the things set up, and the issue is, right, when you, because you have such a for loop in your, like you have this for loop inside of your while loop, you are touching O of n squared quite possibly, and this will literally TLE on like the very last test case. If I'm not wrong, like 77 out of 78 or 78 out of 79, it will TLE because your for loop, right, your for loop is going potentially O of n square. So what we want is, once we're done, right, once we've added these entries, do you think those entries will matter for that particular index anymore? No, right? Because, well, A, we've already processed everything that was possible, and B, even if we do come back to this index, we will have a we will have another check when we do add it in the next part, but we will have a check that essentially states it's already been visited, so there's no point in double visiting a node, right? Because we have a visited set as well. So what we can do is essentially throw away the whole entry, the whole part of the dictionary. So once we are done processing the thing for this particular element, right, for this, we've fetched all the neighbors that we wanted, we will simply clear it so that we don't run a for loop again on it for no reason when we don't want to. Okay, this is the singular trick that will save you the TLE. Now the next thing, I've optimized the code compared to yesterday a bit more. The yesterday one I did have like a consider front, consider back, but this one is a bit more simpler to understand, I would say. But this one, so what I've done here is for next and index -1, index +1. So remember, what I want you to remember is we have like these potential, like we get some I, we get some J, we are sitting at some K, we have K -1 as our approach, K +1 as the other, and the next iteration would needs to like visit all of this, right? So now we will focus on K -1 and K +1 because we've done I and J over here. Okay, so now we have K -1, K +1. That's literally all it. IDX -1, IDX +1. Check the bounds, right? Like I said, don't go out of bounds. And only process the next node if it has not been visited. So and next not in visited, I'll just write it down here. Visited dot add next and q dot append next. And like I said, for every single time we run out of that for loop for the range of length q, we will be hitting a new level. So counter plus equals 1, and at the end just return counter. And that's pretty much it for this question. It is the same thing as 3. There's just a bit of a minor tweak and a bit more on top over here, adding a hash map to get that, and this particular TLE solver.